This is not a GPU. This is my CPU rendering all of this. And all it comes from simple formula. Your screen is flat, so how do we fake depth? It's actually just geometry. We take a 3D point and project it onto a flat plane. Once we do that, we can drop one dimension and draw it on a screen. To make this easier, imagine you're looking straight down the y-axis. Now we are only working with x and z. Let's take a point in space. We want to project it onto a fixed plane in front of the camera. So I built two triangles, one from the original point and one from its projection. They have the same angles, which means they are similar. Because the triangles are similar, the ratios are the same. So we get this formula. We do the exact same thing for y. Now here is the interesting part. As z gets bigger, the point moves closer to the center. That's perspective. Right now the center is at 0, 0, but screens don't work like that. So we shift everything to the middle of the screen. The minus just flip y, so up is up. And that's it. This one simple idea is enough to turn 3D points into a 2D image. And this is already enough to create a starfield. We just generate a bunch of random points in 3D space. Each point has an x, y, and z. Now here's the trick. Every frame we move each point closer to the camera by decreasing its z value. And that is what creates the warp speed effect. When a point gets too close, we reset it back to the distance, so it can fly toward us again, over and over. To make it feel even smoother, I also add a bit of motion blur. And suddenly, it actually looks like a space. Points are not enough to represent 3D object. For that we need models. We will keep things simple. Our model will be a wireframe. Just line connecting points. Let's take a simple cube. We split model into two parts, vertices and indices. Vertices are just a point in space that we can connect with lines. Indices are a pair of numbers. Each pair points to two vertices and define a line between them. This makes rendering much more efficient. A cube has only 8 vertices, but it needs at least 12 lines. And remember, before we draw anything, every point has to be projected. With this setup, we only project 8 points, and reuse them to draw all 12 lines. Because line only refer indices, the same vertices are used again and again. Without this approach, each line would need its own copy of points. That's 12 line times 2 points, that's 24 points. So instead of projecting 8 points, we would have to project 24. And this gets even worse when we start animating objects. Now, let's look on something more powerful. All of this, the square, the solar system, the plane, is not done by applying formula directly. Instead, we use matrices. And they give us a superpower. With matrices, complex motion becomes simple. This entire animation is just a chain of matrix transformations. It might sound scary, but it's actually very simple. A matrix can represent rotation, translation, scaling, camera movement, and projections. And here's the real power. We can combine all of these operations just by multiplying matrices. For example, how do we make the moon rotating around itself, while also orbiting the Earth, while the Earth orbiting the Sun? With matrix composition, we start with the moon at the origin. Then we rotate it around its own axis, move it away from the Earth, rotate it around the Earth, move everything to the Earth orbit, and finally rotate around the Sun. Order matters. The first operation is on the right, the last one is on the left. Once we build this matrix, we can apply it on any point on the moon. Instead of transforming every point step by step, we do it all at once. We calculate the matrix once per frame and apply it on every point. That's much faster. A 3D matrix is just a 4x4 grid of numbers. This is the identity matrix. It does nothing, just like multiplying by 1. Here are the few examples of matrices we can use. Translation, rotation, scaling. We use 4x4 matrices, so we need 4D points. We just add one extra value, w. A 3D point becomes x, y, z, w, which is equal to 1. This is called homogeneous coordinates. To get back to 3D, we divide by W. So different value can represent the same point, like P2482 is the same as P1241. Vectors have W equal to 0. Each new coordinate is a combination of all input coordinates and one row of the matrix. That's why we can represent any transformation with matrices. We can take this even further. We can build a projection matrix that converts 3D directly into 2D. That means we can transfer the moon and project it onto the screen in a single operation. Let's build it step by step. We start in homogeneous space. A point looks like this: x, y, z, w. To get back to 3D, we divide by w. But in our projection formula, we divide by z. So here's the trick. We set w equal to z. We can build a matrix that output w as z. Now after division by w, we are effectively divided by z. We also scale x and y by the projection plane distance. Finally, we move everything to the center of the screen. Screens are not square, so we fix the x-axis with aspect ratio. And that's it. This single matrix does everything. Transfer the object, apply perspective, and maps it on the screen. And matrices can do even more. We can build a camera using just its position and a point to look at. This makes camera movement incredibly simple. You can move it along a path and keep it locked on an object. No angles, no manual rotations. You get all of that for free. But that's a topic for another video. This is just the beginning. There is a lot more behind this, and I will be breaking it down in the next videos.